Recording in progress.
Can you
Okay.
try talking a little louder?
Louder.
Or maybe I could just sit closer.
Yeah, I can try. I mean,
You're usually very loud.
Yeah, I
When
know.
you talks,
Right.
it's like ASMR.
I know. I'm usually, normal volume, but when I talk about math, I'm very soft-spoken for whatever reason.
Looking serious.
I don't know. Yeah. Okay, so today we'll be talking a little bit about ext and tor. We spoke about ext a lot yesterday. We'll do a few calculations, and hopefully at the end I'll summarize basically how derived functors start. Basically, I mean, there's a lot to say about derived functors, of course, but I think, in 2 weeks, there's not much we can say. And next week we should start spectral sequences. So I'll just tell you the recipe for deriving your functor, as they say, at the end. Okay. So let's calculate some X groups for Z modules or abelian groups. We'll just do like the most basic examples so that you can see basically what happens in the most simplest of cases. So, okay, Z modules. So one very nice thing is that X I Z A B is equal to 0 for all I bigger than or equal to 2 and all AB. And how should we see this? So two ways. You can either pick a length 2 or length 1. I forget how length is counted, but projective and injective resolutions of abelian groups can be chosen strategically so that most of the groups are 0. So I'll use a projective one because it's, I don't know, easier for me to think about. So we can choose a projective resolution of A to be this resolution, so 0, this kernel of P, and then f of A, which is the free module on A, and then P is this projection onto A. So it's like this. And so the point is that you may object. The point is that kernel of P is free. You may object and say like, okay, why is this a projective resolution? It's because for abelian groups and if R, I mean, in general, if R is a PID, then submodules of free modules are free. That is a serious fact that we are using here. So I should write this down. It's projective resolution because kernel P in f of A is free. And so the same thing, you can repeat this for, so instead of Z, you can do this for R PID. Okay. And so you have this nice resolution, you apply the contravariant Helm functor. Most of the terms in the resulting cochain complex will be 0, which in turn tells you that most of the X groups are also going to be 0, right? So I'll let you, if you don't believe me, of course, work this out. Okay. Okay. Right. So okay, what's left? X0 and X1. So we should work those out too. So oops. X0Z of, okay, well, we'll do Z mod PZ and NEB. This thing, well, X0 is just HOM, right? So it's just HOM of Z modules. Okay, I'll just suppress this. Z mod PZ into B, but okay, Z mod PZ has one generator, order P. You need to send it to an element of B that also has order P. So, okay. So this is just, so the notation is this, the subscript before the B, P, PB. So this is just the P torsion of B. So this is B and B such that PB is equal to 0. Nice. Okay. Okay, now X1 Z of Z mod PZ with B. What is this? Okay, so now we have to actually use a resolution and calculate something. So we should use a nice resolution of Z mod PZ. Okay, try this one. So 0, Z, multiply by P map, that maps into Z, and then the co-kernel of that is Z mod PZ. And that's surjection. Okay. Z is a projective free Z module. So okay, this is a projective resolution. You apply the hom functor. Okay, so apply the contravariant hom functor. So hom dash B and get. So what should I get? Well, I mean, we're cutting off one of the terms, right? So okay, we should get 0 hom Z B, and then this is this map with an upper star, which means where should it go? It should be pre-compose, or yeah, pre-compose. Pre-compose by multiply by P, and then again hom ZB, and then 0 again. Right. Okay, but remember that these are just B. And if you trace the isomorphism, this is just, again, the multiply by P map. So, okay, then X1 is the cohomology of this. So it's the kernel of 0 mod the image of the multiply by P map. And that's just, okay, that's just B. So what I mean by 0, I mean this 0 map here on the right. B mod PB, PB. Not the subscript one, I mean the P times B. So yeah, okay. So that's the, okay, that's X1. Z of Z mod PZ with B. Okay. Let me just make sure Zoom is okay. Yeah, good. Okay. And okay. I put in Z mod PZ in the first argument. What happens if it's Z? But remember, Z is a free, i.e. projective C module. So since Z is free, X XZ I of Z with B is equal to 0 for I equals 0, 1. Okay, so now remember, what was it yesterday? I said something about how X plays with coproducts in either factor, or coproducts in one factor, products in the other one, coproducts in the first. We are now able to calculate X for modules in the first component that are finally generated. So okay, what's the upshot? We can calculate X I Z A B for A finitely generated. Nice. Okay, and so okay, this is just a remark. Why the name X? So maybe this is your first time seeing X. You may wonder why we even call it X. It might be short for something. Of all the math words out there, what could it possibly be short for? Extreme value? No. Extension? Yeah, it's short for extensions. Okay, so the name for X comes from the following. Well, okay, maybe it doesn't come from the following fact, but it's related to the following fact. So here's a fact. So equivalence, so the set of equivalence classes of extensions of A by B. So what is this? This is if I go down here, this is, you should think of this as just x such that you can form the short exact sequence 0, it should be b and then x, b, x, a, 0. This can be made, exists, right? Extensions of a by b, okay, yeah. Yeah, so the set of equivalence class, okay, you may be wondering what is equivalence class? Equivalence under isomorphism. A by b, this set is in bijection or natural isomorphism with x1 r a b in some way that I will not talk about. You should read about this. It's really cool. Okay, but this is just x1. You may wonder, oh, what does x2 have to do? I mean, what x3? You may have questions. And I will say you should read about them. It's interesting. So ... Okay, cool. So what else can we do with x? So for the topologists, which I don't know if we have any, but the topologists learn about this very important theorem. It's called the universal coefficient theorem in cohomology. And so I will state it in the context of homological algebra, and then I will say what it might look like in topology as an application, I guess. So, okay. Here's the UCT. Don't worry so much about this. It's very specific. I mean, it's a cool result, but this is another place it shows up. A very, very important place it shows up. So UCT for cohomology. So, okay. Let P bullet, the bullet should go under, P bullet be a chain complex. Oops. Chain complex of projective modules such that each image, so each dn pn is also projective. This is a weird, maybe not so weird condition from the point of view of the cohomology theories and homology theories appearing in topology, but this is just something we need. Don't ask me why. Then for any, then for any, every n and R module, and any R module M, there is the following short exact sequence. There is, and this, okay, the other adjective is that the following short exact sequence that I'm about to write down is split, but non-canonically. So there's some choice you have to make the splitting happen. Okay, so there is a non-canonically split short exact sequence. 0, x1. So here's the x group showing up, x1r. And then it's the, okay, so this is going to be a horrible German sausage of an expression of a short exact sequence. So the hn minus 1 p bullet. So the n minus 1th homology of p bullet. So, right, this is a chain complex p bullet. I know in the past I might have written p bullet for projective resolution. So this is not possibly non-zero here. And then m. And then the middle term is now a cohomology term, hn. Here I put hom r p bullet m. So this is this is the cochain complex. So this hom R p bullet m is the cochain complex you get after applying the conjugate hom functor. And then the last term is hom R h n p. There's a bullet missing. Okay. With m. Yeah. And then 0. Yeah, so this is a weird thing, but maybe it may be easier if I write, it may be easier to see what this looks like in topology. So what's the use? In topology, you may want to find the cohomology of a space X with, quote, coefficients in an abelian group M instead of just like Z coefficients or something. And this tells you basically how to relate the original cohomology in the original coefficients, or I guess here it should be, I messed up the order of my words, but I'll write down the result, and this is the point. For cohomology of a space X with coefficients in M, we have, so the splitness, the splitting of the short exact sequence gives us this isomorphism. So Hn xm, that's that middle term. At least this is how they write it in topology. This is isomorphic to hom, and then you put the cohomology here, Hnx with m, and then O plus xt 1z, Hn minus 1 x m. So it's like, basically it's a matter of, do you apply the hom functor before or after you take cohomology, is sort of what's going on here. If you apply the hom functor first in topology, you will get the cohomology of the space X. Whereas here in this after the isomorphism symbol, this hom here is, okay, you apply the hom functor on the homology groups you get after, and it's a matter of, how much do they differ. This is what this is sort of talking about. So yeah, question.
So Hn at H sub n x is Andrew coefficients.
Yeah, the usual homology of X.
Okay, and then the hom sort of being as
Hom is, yeah, dualite, like, I guess, I don't know, I don't remember exactly how algebraic topology goes, but this is sort of, yeah.
So in that case, we're viewing M as a Z module.
Yeah.
It is an R module.
Yeah, here, in topology, yeah, Z module, everything's Z module, yeah.
Right. Oh, okay.
Yeah, everything's abelian groups, I guess, in this topology addendum. Yeah. Oh, man, time 4:23, oh dear. Okay, so now we said plenty about X. Now I have a different, well, I mean, I've spoken about both of the hom functors from earlier, and we found this X thing. You may ask, okay, what about that other functor from before, the tensor product from earlier? You can also do a similar thing to what we did earlier with X. You can do it to the tensor product, and you can get something called Tor. So, okay, what about these tensor products? And, I have written both of them out because if R is not commutative, we have to worry about which side you do the tensor product. Fine. But both of these functors they're both covariant and right exact. Okay. So both of the X functors from before were left exact. Now we're doing tensor product, which is right exact. So something different has to happen. And in the end, we will obtain these so-called Tor groups, Tor I, A, B. Okay, and what's the recipe? It's very similar, so I'm going to be very quick about this. So how to get Tor? Step 1, let's let's say, yeah, take a projective, oops, projective resolution of A, step 2. So call it like P bullet. Oops, that bullet should be down here. And then apply the tensor product functor to it. So apply the tensor product to P bullet. And then like before, okay, so before we took cohomology, now we take homology because P bullet is a chain complex. These are covariant functors, so I guess the descendingness is preserved. So take homology. And that's why in Tor the index, the I goes on the bottom because it's supposed to be a homology, basically. Take homology to get Tor sub I, A, B. And you can also use the other functor, other tensor product to get this. It's like X in that you can use either one. This is a theorem that you can use either tensor product to get this. So instead, you can do it at B. You can apply the other one, a tensor dash, and then again take homology. And it will also get you the same thing. So I will not say more about this. It's like before. I should probably summarize some properties of Tor. They're similar to Ext. There are some differences, but I want to sort of get through this a little bit quickly. So I'm not going to spend too much time on each one. Okay, so Tor defines, so Tor is functorial. Oops. In each component, of course. As before, with Ext, we saw that x0 was just the original functor itself, the original Hom functor. Again, the same thing happens. So Tor 0 of AB is just a tensor B. Nice. Tor preserves coproducts in a particular way. And so here is where the commutativity of the actual ring comes into play. So Tor preserves coproducts in second variable. So for I A with coproduct alpha B alpha. Again, this could be any coproduct, could be infinite. This thing is isomorphic to coproduct alpha Tor I A B alpha. I wrote that down right. Yeah, okay. And colimits as well. So we didn't see this for X, though X should do something similar, but here it is specifically for Tor. Tor I A with colimit B alpha. That's isomorphic to colimit of Tor I A with B alpha. Okay. And so if R is commutative, you can flip it around. Then so this is also true in the first coordinate. But then here it changes to limits and not colimits. Sorry, limits in the first variable. Okay, that's just a fact, fun facts. Okay, so another thing is that if your ring is commutative, then, oops, then Tor is actually symmetric in its components. So Tor I AB is isomorphic to Tor I BA. Nice. And okay, last thing is you get both long exact sequences for Tor. I'm not gonna write them down. They kind of suck. Yes.
So if your ring is not commutative, what happens if you try to repeat the argument in third both length of the first entry?
I don't actually know. Okay. There's probably a very easy answer if you just sit down with the resolution and attempt to do it. So okay, if you try to calculate it with so okay. You can try to start with a projective resolution of, well, either A or B. A projective resolution of a coproduct, you can glue, you can put together projective resolutions of each factor to make a projective resolution of the coproduct. And yeah, I'm not really sure. Something probably can be said, but as far as I was reading this, there is no stated result. I'm sure something should happen, but maybe along the way something breaks. I don't know. But yeah, that's curious question, but homological algebra is so tedious. I don't want to I don't want to sit down with this. Okay. Yeah. So okay, maybe what does the lack of commutativity mean? It means somehow A has to be a right module and B has to be a left module, right? So probably somewhere there something happened. I don't know what happened, but that's the only reason that I can think of. But yeah, it's worth sitting down maybe one day on a free Saturday. I don't know. Okay, long exact sequences. It's 4:30, maybe. Probably shouldn't write them down, but they go something like dot 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 to Tor 1. So if I have a short exact sequence X, Y, Z, I can get a long exact sequence in Tor. Oh, I can get two of them. So two of them, I can get Tor A, Tor AY, Tor 1, AZ. And this connects to A tensor X to A tensor Y, A tensor Z to 0. And then there's a similar one in the other component, also sort of continuing the exact sequence to the left, much like how X continued the exact sequence to the right. Yeah. Yeah, okay. I said earlier also that X commutes with localization in a funny way. Tor also does too. But, okay. So maybe I should say something quickly about the naming for Tor. So Tor, short for torsion. And why should this be true? You can do the following calculation, which I won't do because, well, we did the calculations for X. These are very similar in complexity, and it's not worth going over them again. You should do them. They're chill. So if we pick the ring to be the integers, so okay, Z should go up here, Tor I, and then I can do Z mod PZ with B. I have a few cases. So first case, when I is 0, I'm going to get B mod PB. And then, so this is I equals 0. In the second case, I'm going to get subscript PB. That's for I equals 1. So that's that P torsion elements of B. And then I'm going to get 0 for I bigger than or equal to 2. So very interesting, at least for the case of the integers, it looks like it's like swapped 0 and 1 with X. So that's interesting. You can also repeat this proof for R commutative. So instead of Z, you can pick R to be a commutative ring, and instead of Z mod PZ, you do R mod R mod U, where U is a non-zero divisor. Non-zero, okay. Non-zero, okay. There's a question about where the hyphen goes. Non-zero divisor. I'll just put both in. Yeah, instead of Z mod PZ. And then you'll get B mod UB, and then the U torsion of B. Okay, so that's fun. And so, okay, in general, tor 1Z of AB is a torsion abelian group. That means all its elements have finite order. Then also tor Z n AB equals 0 for n greater than or equal to 2. This is, again, due to this, you just pick a nice projective resolution of A with 2 terms, same as before. And so before I said it for X, you can calculate X for when A is finitely generated. With tor, because the tensor product is, oh dear, I already forget. It's an adjoint of, I don't forget. So it's right exact, so it's a left adjoint. Yeah, it's a left adjoint. It preserves limits. So you can actually calculate tor AB for any abelian A, so possibly infinitely generated, because, okay, so I should write this down. Why can we do this? So we can calculate tor, tor Z I A B for any A, since A is the limit of its finitely generated subgroups, and tor preserves. Okay, it is the case that tor preserves limits. That's also not trivial, but yeah. A is the limit of its finitely generated subgroups. Dot, 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 because this requires some thought. Okay. And so before we spoke about how X characterizes projective and injective modules, you can ask the question, like we asked the question before, like when is X, or sorry, when is HOM exact? And we saw that, like, okay, for projective or injective modules, it was the case that one of the HOM functors, either HOM functor was exact. So now the question is, when is the tensor product exact? That is an interesting question because it is not just projective or injective. You get something different here. So when is the tensor product exact? And the answer is when you tensor with a flat module. So when tensoring. So, okay. What I mean is the functor that is tensoring with a flat module, that is, yeah, so tensoring with a flat module. So I should talk about what flat is. Okay, I should unpack what this meant. I mean, here is that, so again, we have to worry about left and right here. So the left module, so left module B is flat if the tensor product in the second component is exact. And then you can do right here. If so, instead of this, the right module A is flat if A tensor dash is exact. Okay. And so, okay, what modules are flat? Well, for one, projective modules are flat. That is true. And that's sort of by design, at least when we were calculating Tor. You can calculate Tor and C, Tor 0. So, okay, projective modules are flat. But the proper containment. So projective modules are flat, but it's proper. There are flat modules that are not projective. So in Z modules, here's an example that also requires some unpacking, so I won't. Q is flat, but it's not projective. So Q, when you tensor with Q, that's exact, but Q is not projective, so you can probably prove something like, oh, Q is not a direct summand of a free Z module. You can probably prove that using some ring theory. Not super bad, but yeah, it's like that. And so, okay, like the result with X, we should have a similar one where B is flat if and only if the higher derived functors vanish on it. So, okay, the following are equivalent. So B is flat. This agrees with for I AB is equal to 0 for I greater than or equal to 1 and any A. And then just the first Tor group will also work. Tor 1 AB equals 0 for any A. Okay. 441. Something wrong in Zoom? I have this weird feeling that some people cannot join. Okay, no matter. I don't know. I got an email for some reason. But someone was trying to join. I don't know why. What? I don't know. Okay, right. Okay, so maybe I should say a little bit more about flatness because it's a sort of weird thing that it's different from injective and projective. But there is a connection between flatness and injectivity in the following way. And it's in a way that I think is really cool because this sort of thing that's going to come up is always very nice for me to see. So here's some curious results, which maybe since I don't have time, I'm not going to say too much about them, but okay. So here's a definition. So curious. So for a left module, left R module B, you can define what's called the Pontryagin dual module for B. The Pontryagin dual of B is the right module, the right R module, which is given by, so hom in AB of B into Q mod Z. So, if you've seen this before, this is, I mean, you might have seen something like this if you've done any representation theory or Fourier analysis. It's a very curious thing that has come up. Q mod Z you should think of as some prototype for the circle, something like that. I will not say more about this. You should ask me afterwards, or I should ask people who know more about this, because this is very curious to me. I'm very unknowledgeable about these things, and I would love to know more about this Pontryagin dual, at least in this setting. Okay, so it's defined this way, and you may be wondering what the right R module structure is. So so if I have a function f from B to Q mod Z, then FR applied to B is equal to f of BR. That's the R module structure. And so the lemma is that, so one lemma that we need is that f from B to C is surjective, or sorry, injective. I guess it doesn't matter if I wrote surjective. If and only if the dual map, so f star from, sorry, I use the star. This is called B star. F star from C star to B star. So this is, question.
Should that be F of RB?
Oh, yes, RB. Yes, my bad. Thank you. Yeah. Thank you. So yeah, so F from B to C is injective if and only if this dual map F star from C star to B star, which is the one you get after applying the contravariant hom with Q mod Z, if this map is surjective. Not a bad proof because, okay, Q mod Z is an injective module, so hom AB dash Q mod Z is exact. So, okay, look at the exact sequence, 0 cur F B C0 dot, apply the contravariant hom functor. You'll find that the co-kernel of this F star is the dual module of cur F, but you can show that, okay, dot, A is the zero module if and only if A star is the zero module. So not bad, cool. Okay, so now you can show using the tensor homojunction that B is flat if and only if B star is injective. That is cool. And oh man, I want to say more about this, but okay, I will not. I can talk about this another time. The proof is just use tensor adjunction and the lemma above. It's really cool. I thought this was a very slick result. And so you can use this result and some more details, actually. I think this is not so obvious from just this alone to show that the flat Z modules coincide with the, they are the torsion-free C modules. Cool. Okay, so that was a cool detour, I guess. Back to going to Tor. So here's another interesting fact, which I will come back to actually in a bit. We can use what's called a flat resolution instead of a projective resolution to calculate the Tor groups. So, right, projective is contained in flat, so you have now a bigger collection of modules that you can try to resolve with. So it could possibly be easier to calculate Tor using a flat resolution. So I should write this down. We can use a flat resolution instead of a projective one to calculate Tor. So flat resolution is just, at least in this setting, since it's going, they're replacing the projective ones, it's so F lower bullet goes into A, say. And this is an exact sequence with the Fi flat, dot. Just like before, except flat instead of projective. Okay. 10 minutes. A few things left to say. Okay, so we've spoken quite a bit about X and Tor. How do you, I mean, now if I just give you a random left exact or right exact functor, can we do a similar thing as before? The answer is yes. These are called derived functors. So I'll write down the recipe. Which the recipe is the definition. So derived functors. So okay, we'll do it for right and left exact. They're very similar. So f from a to b, if f is a right exact functor of abelian categories, then you want to form a projective resolution. So I have to, you have to assert that A has enough projectives before you can do something like this. So if A has enough projectives, then form the left derived functors. So this is L sub I F, also going from A to B by the recipe. So this is L sub I F on A. That's by definition going to be the homology. So H sub I of F applied to a projective resolution. So this should be down here. Yeah. Where P bullet is a projective resolution. And okay, it can be projective or something called F acyclic, which I will also define once I'm done writing this. So, or F acyclic resolution of A. Yeah. Yeah, and okay, F acyclic just means that in the resolution, so an object Q is F acyclic. If the higher derived functors vanish on those objects. If L sub I F on Q is equal to 0 for I greater than or equal to 1. So I guess in order to know if something is F acyclic, you need to first calculate the higher derived functors using a projective resolution and then test it against an object and then see. Yeah. And then once you know that these are F acyclic, then you can use those objects in a resolution if you like. Okay, so right, so Tor is the Tor I are the left derived functors for tensor product or the other tensor product. And then okay, now I have to flip it around. If I have a left exact. I have a left exact functor of abelian categories. If A has enough injectives, then the right derived functors. This is R upper I F from A to B. These are given by R upper I F on, I'll just say B. This is by definition the cohomology of F I upper bullet, where I upper bullet is an injective or F acyclic resolution of B. And then here, if you have a left exact functor, F acyclic means R sub I or R upper I F of Q is 0 for I greater than or equal to 1. It's like the same. So that, like before, we did it with we did that with x, so that is to say x upper I is the right derived functor for the hum functor. Yeah. Okay, so that's just how you derive functors. So this is cool. Okay. And so these derived functors enjoy many of the same properties that we saw from before. You can form long exact sequences, just like for ext or tor. I won't write them down. You can imagine what they look like. Instead of ext and tor, you just write L sub if or R upper if in place of those. And then what else? You know, L sub 0 f is just f. And then R's upper 0 f agrees with f when f is left, right, exact, whatever. Another interesting thing that we saw with ext, actually, that I will say more generally here for left exact f. So is that, okay, so if I have a left exact f, then R upper if agrees with L lower I, Li f up, and then I op that again. So we saw this for the contravariant hum functor. So that was interesting, and it's similar the other way too. I'll let you do that. Okay, so I'll just end today with an exercise that I'm not going to prove, but I want you to look at this exercise and attempt this. It's a good exercise. You need to prove something like this in order to show that you can actually use F acyclic resolutions instead of just the projective or injective resolutions. So maybe I have it here. So it's called dimension shifting. Oh dear, okay. I hope you can see all of that. Yeah, so if I start with an exact sequence MPA 0, there's just some way to relate the derived functors of f with the previous derived functor of f applied to m instead of a. And so, you know, this sort of result doesn't look like super interesting, but it's part of the recipe that you need in order to use an F acyclic resolution instead of just a projective or injective resolution. And yeah, I think that's a good place to stop. Thank you. See you next week. We will start talking about double complexes in our journey for spectral sequences.